Okay, good morning to all. So today we are going to see the topic that is evaporators. Okay, just a second, 1 minute. Okay, we will start. Okay, good morning to all. So today we are going to see the topic that is evaporators. Okay, just a second, 1 minute. Okay, we will start. Okay, good morning to all. So today we are going to see the topic that is evaporators. Okay, just a second, 1 minute. Okay, start. So today we are seeing the topic that is evaporator. Just a second, 1 minute. Start. So evaporators mean basically it is a special type of heat exchanger. Okay. They are special type of heat exchanger. Am I audible? Am I audible? Okay. Okay, Rio. So evaporators are special type of heat exchanger. So we have seen in last class what is heat exchanger and what is the use of that heat exchangers. Okay, in the real application. Okay, that we have seen. So evaporators basically used for the concentration. Okay, for the concentration of juice or anything in which there is huge amount of water is present. Okay, in which there is huge amount of water is present, there we use the evaporators. Okay, so you can write it, they are special type of heat exchanger. They are known as special type of heat exchanger. Okay, so we know that uh, when something will evaporate, vapors will be formed. Okay, and that vapors are responsible for creating a pressure, and that pressure is known as vapor pressure. Okay, so it is the pressure exerted by vapor molecules on liquid surface. Okay, and that is known as vapor pressure. Okay, so our boiling point is a function of vapor pressure. Okay, boiling point is a function of vapor pressure, or you can say boiling point is a function of amount of solid present in that, amount of solid present. Okay, so if I compare two components A and B, suppose the boiling point is, this is 70 degrees centigrade and this is 150 degrees centigrade, and you are at suppose 100 degrees centigrade. The system is at 100 degrees centigrade of heat you are supplying. So what will happen? 70 degrees centigrade, more vapors will be formed. Okay, because it is more volatile, more vapors will be formed. It means that early the boiling point will receive. Okay, so we can say that boiling point decreases if vapor pressure is more. Hai. Boiling point decreases if vapor pressure is more, because boiling point will occur when it will, okay, when it will match with the system. Okay, when which will match the atmospheric system. Okay, and it will match with the atmospheric system, that is the boiling point. Okay, so we will see what is boiling point curve and all that. So but here boiling point will decrease when the vapor pressure will increase, because if it is more volatile, it means more vapors will be formed. Okay, if it is more volatile, it means vapor will be formed. Okay, so we will do one example. In evaporator, what is happening is that you have a container in which A and B are miscible with each other. A and B are miscible with each other, and A is volatile and B is non-volatile. Okay, A is volatile and B is non-volatile. Okay, so what is happening? What is happening here? What is happening here? The condition is like this. So A is volatile, so A will take part in the evaporation, or you can say vaporization. A will take part in the vaporization. And what is B? B will not take part in the vaporization because B is solid and B is non-volatile. Okay. So if you see, in ideal condition, the surface available for the vaporization is 50%. Okay. Surface available for the vaporization is 50%. Okay, surface available for the vaporization is 50%. And for condensation, means now A is at the vapor, so at equilibrium, A will try to condense. So A will come to its own surface A, and A will come to the B will also, because A and B are miscible with each other. So for condensation, surface will be same. That is 100%. Okay. For condensation, surface will be same as 100%. So what is happening? For vaporization, it is 50%, and for condensation, it is 100%. Okay. So it means that less vapors are forming, less vapors are formed. So as less vapors are formed, so we have seen as boiling point decreases when vapor pressure increases. So here, vapors are getting formed are less. So it means boiling point will increase. Boiling point will increase. Boiling point will increase. As boiling point will increase, what is going to happen? There will be elevation in the boiling point. There will be elevation in the boiling point. So how much this is going to increase, that is boiling point. How much boiling point is going to increase? that totally depends upon the depends upon the solid composition, how much solid is present in the system. Okay, how much solid is present in the system. If more solid is present in the system, there will be more elevation of a boiling point. Okay, if more solid is present in the system, then there will be more elevation of a boiling point. So this is the reason for elevation of a boiling point, because solid is not taking part in the vaporization. It is only taking part in the condensation. So that is why for vaporization, solid surface is decreased. So vaporization surface is decreased. Okay, and condensation surface is same 100%. So means less vapors will be formed, and we have seen that the component which have a less vapors, it has a more boiling point. Okay, it has a more boiling point. Got it? Okay, for condensation, how it is 100% available? See, you have like this, elements are present. A is volatile, B is non-volatile, A and B are miscible. Okay, A and B are miscible. So when you are giving heating to the surface, A will go up, A will take part in the vaporization. So how many molecules are moving up? 50%. Okay? I'm taking it, considering it as ideal condition. Okay. Because B will not go. B will take energy, but it will not take part in the vaporization. Now at equilibrium, A molecule will come down. So A molecule will come down to its own molecule A, and A will also go to B towards, because A and B are miscible with each other. This A will also come down, and this A will also mix with B also. A, B, A, B. So is there any difference in the condensation process? No, condensation process is as usual. It is happening. But vaporization process is decreased. Less vapor molecules are forming. So that is why as vaporization decreases, condensation as it is same. So this is the reason there will be elevation in boiling point. Okay. Done? Understood, Rio? Okay. So what is happening in the evaporator? Here you are providing the steam, mass of steam into steam. Here the heat is moving on, P1. Here solid plus liquid is going. Your product coming in terms of more solid, okay, plus liquid, liquid will be less, and vapor is moving, okay, and vapor is moving. So here there are terminologies: capacity, how much water is evaporating from the feed, then we can do the material balance, or you can say mass balance. It is feed equals to product plus vapor. So this vapor is nothing but the capacity, how much water is evaporating. Now we can do the solid balance because solid is present in the feed and the product also. So mass of feed, solid present in feed, xf equals to product into xp. So this is solid balance. Okay. Now there is a term economy. Economy is vapor generated upon steam in the feed section. Okay, steam supplied in the feed section. So a good heat exchanger is that who has a more economy. Okay. Okay. So if we do the energy balance can be done here. Energy balance at the process side means how much heat we need. Okay. So here again mass of steam into enthalpy. Same thing, vapor is coming. Here your product is coming. Your feed is moving. Here is the supply. So if it is P2, it is P1, then obviously where the steam we are supplying, it is P2 is greater than P1. So rate of heat supply is equals to how much heat we need, that is mass of feed into Cp of feed, Tb minus Tf plus mass of vapor formed and lambda. Okay. That is the rate of heat supply. This is feed. This is product you are getting. This is vapor which is generated, and this is the steam we have supplied to the system. Okay. So MCP delta T, what is this? This is the heat which is given to the solid material. That solid material, how much heat it will consume, plus MV into lambda 1. What is MV? MV is how much vapors are generated. So that is the total amount of heat in the process side. Hana? This is the total amount of heat in the process side. Total amount of heat in the process side. Okay. So you can write this. We can do the overall energy balance also. Overall energy balance, that is mass of feed into enthalpy of feed plus mass of steam into enthalpy of steam that is supplied. Here it will be mass of product into enthalpy of product, mass of vapor into enthalpy of vapor, mass of steam into enthalpy of condense. That steam will condense. Okay. So here we will write mass of feed into enthalpy of feed plus mass of steam, HS minus SC will give you mass of product into enthalpy of product plus mass of vapor into enthalpy of product. So this HS minus SC will be lambda. Latent heat required. Okay, that is the latent heat required for vaporization. This lambda is latent heat required for vaporization. Steam side. Okay, this is the overall energy balance. So from this diagram, we can say what is happening in the heat exchanger is that here, suppose your steam is moving, and when steam is coming in contact with the tubes, okay, tubes in which the juice is available, and then they are condensed. Okay, they are condensed. Okay, so this is steam, and when the steam lost its latent heat, it will condensed. Okay, and in tubes in this yellow color, they have a tubes in which what is happening here, there will be vapors will be generated. Okay, here vapors will be generated, and at bottom you have a concentrated juice. How these vapors are generated? Because inside the juice there is a huge amount of water. Okay, now this vapors will act as a steam for second one if you are using a multiple effective operator. So on the basis of this, we have done the overall energy balance. On the basis of this, we have done the overall energy balance. See, feed, here you have a feed. So this is feed. Steam you have supplied. This is the steam. You got the product, concentrated juice. You got the vapors. This is the vapors. You got the condensed. This is the condensed. Okay. So on the basis of this, we have done. Okay. So write this. Hello. Hello. Okay, so now we will, sorry for interruption. Actually, due to technical issue, there is a problem. So now we will see the questions. Okay. An aqueous NaCl solution, 10% weight, is fed to a single effect evaporator at a rate of 10,000 kg per hour. It is concentrated to 20% weight of the solution. The rate of consumption of steam is 8,000 kg per hour. What is the capacity? What is the capacity and the economy of the evaporator? Okay, solve this. So in this question, we can do first how much feed is entering. That is feed equals to product plus vapor. Feed is 10,000, product plus vapor. So now we can do solid balance. Solid balance, how much? 10,000 into 0.1. In product, it is 0.2 into product. So product is coming 5,000. So how much vapors are evaporated? That is the capacity is 5,000. Okay. And economy is 5,000 vapor generated upon steam feed equals to 8,000. That is 0.625. Okay. Check this. Have you got this answer? Done. Next question. An aqueous NaCl solution having 30% solid is evaporated to 80% solid. Feed rate is 5,000 kg per hour. Calculate capacity and steam concentration per kg if economy is 0.45. Calculate this. So here again feed equals to product plus vapor. 5000 equals to product plus vapor. So 5000 into 0.3 equals to product into 0.8. So P equals to 1875. V equals to 3125. Economy equals to vapor plus steam, that is it is 3125 upon 0.45. So how much steam fed equals to 6945 kg per hour. So that is what asked in the question. Steam concentration per kg. So it is 6945. Got the answer? Rio? Okay. Next question. It is desired to concentrate 28% of salt solution 30% salt solution in a evaporator. Consider a feed of 300 kg per minute at 30 degrees centigrade enters the evaporator. The boiling point of the solution is 1110 degrees centigrade and latent heat of vaporization is 2100 kilojoule per kg. Specific heat of the solution is 4 kilojoule per kg Kelvin. The rate at which the heat has to be supplied in kg per minute to the evaporator is. Solve this. So in this question, you have to calculate the amount of heat at the process side, है ना? So it will be Q equals to mass of feed into Cp of feed, Tb minus Tf plus Mv lambda 1. So it is equals to 300, okay, into 4. So everything is kilojoule into 110 minus 30 plus 100 into 2100. Okay, so this will give you answer. Solve this. So answer is 306,000. Okay. Next, give heading multiple effect evaporator. Yes, Rio. Multiple effect evaporator. In multiple effect evaporator, what we are doing? The steam which is moving, it is condensed, and the vapor which is coming out from the first will be the steam for the second one. Okay. Again, it will condense down. Same thing for the third one, like this. This is 1, this is 2, this is 3. So this is known as feed forward evaporator. Feed forward evaporator. Okay. So what exactly happen in the feed forward evaporator? The vapors which are generating in the first evaporator will act as a steam for the second evaporator. So as we are moving from 1 to 2, 2 to 3, the concentration of solid is going to be increased. So we have seen that when the concentration of solid is going to be increased, what is happening? When concentration of solid is going to increase, what is happening? The most important thing is that, okay, the most important thing is that, okay, that there is an elevation of boiling point. There is a elevation of boiling point. There is an elevation of boiling point. Okay. As there is an elevation of boiling point, it means more energy is required. Okay, it means more energy is required when there is increase in the excess. But if I compare xx1, xx2, xx3, so xx3 is greater than xx2 is greater than xx1, means xx3 is the highest one. But the steam quality which we are getting in the first one is highest, because here we are getting a pure steam. Why we are calling it as pure steam? Because it is directly coming from the boiler. Okay. But in the second evaporator, the steam which we are getting, it is generated in the first evaporator. So that is why it is not pure. It has some impurities. Okay. Because evaporator is not a 100% efficient system. Some solid impurities may go with the steam, and that will leads to decrease the quality of the steam. But according to theory, what we want is that at the last evaporator, we need a pure steam. But at the last evaporator, we are getting a impure steam. Okay. So this is feed forward evaporator. So for this, to sort out this problem, what we do? We do backward feed evaporator. Okay, what we do? We use backward feed evaporator. Backward feed evaporator. So what is happening in the backward feed evaporator? Same thing. The only thing is that we are introducing feed from the backward side. Okay. So now this is XX1, SX2, XX3. What is XS? It is the concentration of solid. Now we know that XX1 is greater than XX2 is greater than XX3. And you are entering the pure steam. You are giving pure steam to this first one. Okay. So this will help to enhance the evaporation. But again, there's a one problem is that as you are entering first steam, so P1 is P2, P3. So we know that P1 is greater than P2 is greater than P3. Now what is happening here? If P1 is greater than P2 is greater than, for feed, you are moving lower pressure. Okay, for feed, you are moving from lower pressure to higher pressure. So this can't be possible. So that is why for the movement of a solid, you need a pump here. Okay, you need a pump here. That pump will take care of the movement of a solid. It means that if some substance which have a huge solid, then it will be difficult to use a backward feed evaporator. Okay, so backward feed evaporator, what is the advantage? That the system which contain a high amount of solid is getting a pure steam. Okay, is getting a pure steam. Got this point, everyone? And at steady state, if this is Q1, this is Q2, it is applicable for backward, and U1 A1 delta T is equals to U2 A2 delta T is equals to U3 A3 delta T. Okay. Delta T1, delta T2, delta 3. At steady state, you can write this. Okay. At steady state. Got it? Rio, got it? Point. Okay. So this is all about the evaporators. Okay. Now give the heading boiling. Okay. When the temperature of a liquid at a specified pressure is raised to the saturation temperature Tsat, at that pressure boiling will occur. Okay. Boiling occurs at the solid liquid interface. When a liquid is brought into contact with the surface maintained at a temperature Ts sufficiently above the saturation temperature Tsat of the liquid. Okay. So here Q of boiling is equals to H Ts minus Tsat. That is H delta T excess. So here you have a container. Here you have heating element. Water Tsat equals to 100 degrees centigrade and this surface is at 110 degrees centigrade. So there will be formation of bubbles. Delta T excess is equals to T surface minus T saturation. The surface tension decreases with increasing temperature and becomes zero at the critical temperature. Okay, so there is a boiling curve which is very important that we will see. Like this. ओके, सो बॉइलिंग पॉइंट ऑफ कर्व की बात कर रहे हैं हम यहाँ पे। सो कर्व कुछ इस तरह से जाएगा, देखो। This is B point, this is A point, here it is started. This is C point, this is D point, and this is E point. So here it is natural convection boiling. This is this total one is nucleated boiling. This point is transition boiling, and then it is film boiling. So the important is the first one is natural, followed by nuclear, then it is film boiling. Okay. Here it is Q, here it is delta T excess. So here it is approx 5, then it is 10, then it is 30, then it is 120, and it is 1000. So what exactly is happening is that initially जब boiling start होती है तो छोटे छोटे bubbles आते हैं, है ना, छोटे छोटे क्या आते हैं, bubbles आते हैं उसके अंदर. So इनिशियली जब बबल्स बनना स्टार्ट होते हैं, दे डोंट हैव दैट मच ऑफ अमाउंट ऑफ एनर्जी, उनके पास उतनी एनर्जी नहीं होती है. ओके, दैट डोंट हैव अ दैट मच अमाउंट ऑफ एनर्जी. ओके, ओके, और यहाँ पे बबल राइज. तो ये यहाँ पे जब उतनी अमाउंट ऑफ एनर्जी नहीं होती है तो वो क्या हो जाते हैं, कोलैप्स हो जाते हैं. बट व्हेन यू फर्दर इंक्रीज द टेम्परेचर नियर टू द सैचुरेशन पॉइंट, बबल्स क्या करते हैं, राइज करते हैं. इसलिए सी पॉइंट पे सबसे ज्यादा क्यू की वैल्यू होती है. ओके, एट सी पॉइंट देयर इज अ मैक्सिमम क्यू. तो इसको हम क्या बोलते हैं, क्रिटिकल हीट फ्लक्स भी इसको हम बोलते हैं. व्हाट वी से, क्रिटिकल हीट फ्लक्स. after some time what will happen, that bubbles will collage with each other, है ना. छोटे छोटे बबल्स मिलके बड़े बबल्स बन जाते हैं. तो उनके पास फिर से उतनी एनर्जी नहीं होती है कि वो ऊपर लिफ्ट हो सके. दे डोंट हैव दैट मच अमाउंट ऑफ एनर्जी अगेन टू लिफ्ट अप. सो अगेन व्हाट विल हैपन, फ्लक्स नीचे आ जाता है. लेकिन व्हेन यू फर्दर इंक्रीज द टेम्परेचर, सो यहाँ पे हम 1000 डिग्री सेंटीग्रेड के पास जा रहे हैं, इट मीन्स वी आर गोइंग टुवर्ड्स रेडिएशन, है ना. लेकिन इस डी पॉइंट पे हमारा फ्लक्स मिनिमम होता है, दैट उस पॉइंट को हम बोलते हैं लेडन फ्रोस्ट पॉइंट. सो एट लेडन फ्रोस्ट पॉइंट पे क्या हो रहा है, हमारा Q इज मिनिमम, और क्रिटिकल पॉइंट पे क्या हो रहा है, Q यहाँ पे क्या है, मैक्सिमम है. ओके, क्रिटिकल पॉइंट पे Q क्या है, मैक्सिमम है. ओके, एट क्रिटिकल पॉइंट द Q इज मैक्सिमम. ओके, सो यहाँ पे ये है Q मिनिमम, एंड एट दिस क्रिटिकल पॉइंट पे क्या है हमारा, ये मैक्सिमम Q है. ओके, सो इनिशियली क्या हुआ, छोटे छोटे बबल्स आए. whole process I will tell. Initially the smaller bubbles will come in natural boiling. In natural boiling they don't have that much amount of energy that they will lift their self. After some time when the temperature is reaching near the saturation point, they will have that much amount of energy and the bubbles will rise. So when the bubbles will rise, you will reach to the C point. But after some C point, the small bubbles will collage with each other and they will form a bigger bubble. Again, the system doesn't have energy, that is the flux will decrease. And then again, if you increase the temperature, but you are going towards radiation, which huge amount of, tremendous amount of energy is required, then your flux is increasing. So if you see from point C to D, you are just burning amount of energy, है ना? Means temperature तो increase कर रहे हो लेकिन flux decrease हो रहा है, ठीक है? So up to point C to E, it is known as burnout period. Okay, it is known as burnout period. Why it is known as burnout period? Because here you are just burning the energy. Okay, here you are just burning the energy. Okay, here just burning the energy, but there is no enhance in the Q value. Okay. Got this point? So draw this diagram. चलो हो गया. So it means that critical after critical point, you that critical point is known as burnout point also, because after that you are just burning the energy, but there is no profit. Means you are not enhancing the Q value. Okay. Okay. So this is about the boiling point curve, which is very famous. Okay. The most important thing where it is a very good heat transfer, it is in the nucleated boiling. Okay. It is in the nucleated boiling. And minimum in the latent frost point. Okay. Then we will see condensation. What is condensation? Condensation occurs when the temperature of a vapor is reduced below its saturation temperature, Tsat. This is usually done by bringing the vapor into contact with a solid surface whose temperature Ts is below the saturation temperature Tsat of the vapor. Okay. So condensation occurs in two ways, that is film wise and drop wise. Film wise and drop wise. So in film wise, what is happening? There will be the formation of a film. Once the film wave is happen, there will be very less penetration. Okay, the heat will not go due to, because the thickness is there, it will create a resistance. In drop wise, what will happen? There will be drops. There will be drops. Okay. So in drop wise, new surface area is always available for the condensation. But here, if you see, there will be thickness of a film. So surface area is not available for the heat transfer. So that is why film wise is not good. Okay. Film wise condensation is not good. But again, drop wise is ideal condition. It is not possible always that drops will be formed. Okay. So heat transfer coefficient of drop wise is 10 times of heat transfer coefficient of film wise. When the non-condensable gases are present in the condensers, again they will create a resistance. Okay, and they will reduce the condensation. So that is why non-condensable gases are also not good. Then okay. So next and the last topic give heading radiation. Okay, so it is the third mode of heat transfer. Okay, so radiation is a third mode of heat transfer. Okay, radiation is the third mode of heat transfer. We have done with the first and the second, that is the conduction and the convection. Okay, so radiation, basically for conduction, we have seen medium is required and medium is not moving. Okay, but for convection, we have seen the medium is required and medium is moving. Radiation, no medium is required. Okay, there is no need of medium. It can travel through vacuum also. So if medium is there, it's okay. If medium is not there, then it is also okay. Okay, and it is interesting that radiation heat transfer is occurring between two bodies separated by medium colder than both bodies. Okay, example is that sun rays are coming. So sun rays are coming to the earth's surface also. It is not that all are moving to the Himalaya or very cold regions. If this is happening, then no rays are moving. The temperature of earth's surface is not same. Okay, it means that the in radiation, what is actually is happening is that sun rays are traveling their own path. They have own path. Whoever will come in between that, they will get the heat. Okay, they will not change their path. Okay, in conduction and convection, we are happening that delta T is the prominent driving force. So here delta T is driving force. It is okay, but it also depends upon the wavelength and all that. Okay, that is the new interesting thing for the radiation. Okay, because you can see that the upper part of our earth surface has a colder region. Okay, if the altitude increases, so if it is a colder and hotter, then all the sun rays will go there, but it is not happening like that. Okay, so there are, it depends on different types of wavelength. Okay, so the short wavelength gamma rays and x-rays are primarily concerned to nuclear engineers, while the long wavelength microwaves and radio waves are of concern to electrical engineers. Okay, I mean depends different types of waves. Okay, next is black body. A black body is defined as a perfect emitter and absorber of radiation at a specified temperature and wavelength. No surface can emit more energy than a black body. Okay, so the surface will be like this. This is of real body. Sorry, this is ideal body. And here it is a real body. So here it is, energy will be given by sigma. Sigma is Stefan Boltzmann constant. That is why it is Stefan Boltzmann law. Stefan Boltzmann constant. Okay. Which is equals to 5.67 into 10 to the power minus 8 watt per meter square Kelvin to the power 4. What is the difference between reflectivity and emissivity? Yes, I will tell you. See, reflectivity means basically what will happen? It will come here as the surface is opaque. It will not transmit, it will directly reflect. This is reflect. Emissivity is that first it will absorb. Once it is done with the absorption process, then it will emit. That is why a black body is a good absorber and emitter, because he has taken, the black body has taken first the energy, after that it has emitted. Got it, Rio? Okay, we will see this in detail also. Okay, we will do one derivation and all that. Okay. So next is Wien's displacement law. What is happening in the Wien's displacement law? Okay, so wait. Before that, we will see Planck's law. Okay. Planck law. Okay. It is the amount of radiation emitted by black body at an absolute temperature T per unit time per unit area about that wavelength. What does it mean exactly is that if any wavelength which has a okay huge amount of energy, okay, it will travel a shorter distance. Okay, so I will draw one graph. From that you will be clear. See 0.1. So here it has a huge wavelength, that is approx 10 to the power 8 watt per meter square microamp. That is the amount of energy it has. Means the way rays which have a huge amount of energy will travel a shorter wavelength. It means that which will travel a longer distance will have a low amount of energy. Okay, will have a low amount of energy. It is approximately you can say it is 10 to the power minus 2. Okay, it is 10 to the power 8, so it is 100. Wavelength unit is mu m. Okay, means the rays which have a high amount of energy, okay, the rays which is coming from the sun which contain a high amount of energy will travel a shorter distance, will have a short wavelength. That is why the sun rays which are coming to the earth's surface, they are traveling a huge, okay, they are traveling a huge distance, but they contain a low amount of energy. Okay, they contain a low amount of energy. So that is why you can say lambda is directly proportional to 1 by T. Right? Lambda is directly proportional to 1 by T. Got it? Got the point? And according to Wien's displacement law, they have given Wien's displacement law, lambda T maximum will equals to constant 2897.8 mu mk. Okay, means if you know the lambda, you can easily calculate the corresponding temperature from this. Okay, so it means that a larger fraction of radiation is emitted a shorter wavelength at a higher temperature. Okay, shorter wavelength, higher temperature. Low temperature, higher wavelength. Okay, so that is why our temperature of earth surface is controlled, because the wave rays which are coming, okay, the waves which are coming from the earth from the sun, they contain a less amount of energy. Okay, Got it? This is a very important point. Next is the Kirchhoff's law. At thermal equilibrium of the two bodies, the ratio of total emissivity to absorption is constant. That is, emissivity upon absorptivity is equals to same. Now you got it, Rio? Okay, emissivity is first you have to absorb, okay, then it will emiss. And reflectivity is directly opaque object will reflect, that is transmit. Okay, reflectivity. Okay, so how much total energy will have any system? One rays is coming, one is getting transmit, one is getting absorbed, and one is getting reflected back. Okay, like this. So how much total energy it has? It is equals to 1. And it is equals to absorptivity plus transmittivity plus reflectivity. And it is get reflected back, it is absorbed, it is transmitted. Okay, so better you do it by alpha. Like this. Okay, so Kirchhoff's law tells that, sorry. Okay, so Kirchhoff's law tells that at thermal equilibrium of two bodies, the ratio of total emissivity to absorption is constant. Means whatever the energy it will take, it will give it back. So we have actually three bodies. First one is black body, in which alpha absorptivity equals to emissivity equals to 1. Then we have gray body, absorptivity equals to emissivity, but it is not equals to 1. And third is normal body. Like this. So we have these three bodies. Done. Okay. So we have done with all the laws, how much energy it have. So any opaque, if opaque body is there, so at that condition, tau is equals to 0. Okay. Transmittivity equals to 0. Then we will see now view factor. Okay. View factor is nothing but one object, the rays is coming. So we have known that how much energy from one object is going towards second object and from second object towards one object. So that is view factor. Okay. So we have to calculate this. It is known as shape factor also. It is known as shape factor. So it is theorem 1, where it is F11 plus F12 plus F13 plus F14 is equals to F1n. Then we have a reciprocating theorem also. A1 F12 is equals to A2 F21. Okay, like this. I will solve one question. Then you will be comfortable with this topic. So suppose you have sphere inside the cube. Okay, like this. So this is 1, this is 2. Okay, or okay, better I will give you one easy example first so that you will be comfortable more. take this. So here you can see that this is object 1, this is object 2. Here the energy is moving like this. Okay, so here F11, what will 1 will represent from object 1? If the same energy is going towards its own object, so F11 is 0. Okay, because it is the bottom part. But from second object, there the self view factor for second is not 0. See, here it can go to its own object. Okay, so we know that F11 is 0, then F12. Energy from one object going towards 2 is 100%, then it is 1. So now you can use F21 into A2 is equals to F12 into A1. Okay, so equals to F21 into 2 pi r square is equals to 1 into pi r square. So F21 is equals to 1 by 2. Okay. Then we have F12 into A1 is equals to F21 into A2. So F12 into pi r square is equals to F21 into 2 pi r square, like this. Okay, same thing I am calculating. F1 is coming 1 by 2. Here area 1, F12 we already got 1. See here, F11 is 0. It means F12 is 1. So F21. So we know F21 plus F22 will be equals to 1. So F22 will be equals to 1 by 2. Okay. This is the object like this. So when this object is moving from this section, okay, so this is object 1. So self view factor of 1 can't be this like this now. The sun ray, the rays can't go like this. Okay, it will be always going in this direction. What is the meaning of F11? From object 1, how much energy is going towards its own object 1? So from this diagram, you can see that every rays is going towards the second object. Okay. Is coming 1. Now I think it's okay. Got it, Rio? Okay. Okay. So now we will do one more question so that you will be comfortable. Okay. Sphere inside sphere. Okay. Sphere inside sphere. Like this. Okay. So if sphere is inside sphere, so this is object 1, this is object 2. So this 1 again, F11 will be 0. Hana? F11 will be 0. Then F12 is equals to 1. Then you calculate other values. It will be F11 F12 into A1 is equals to F21 into A2. Okay, so it will be 1 into 4 pi R square is equals to F21 into 4 pi twice of R square. Okay, so from here F21 is equal to 1 by 4 and F22 is equals to 3 by 4. Okay. Okay, so again see in this diagram, here it has a radius r and it has a radius of 2r. Okay, so basically if it is a 1, okay, if it is a 1, it means that self view factor for this will be, okay, self view factor for this will be equals to 0. No radiation is coming from its own. Okay, because always remember that whenever the object is inside, obviously no radiation will come. Done. Okay. Now suppose you have a solid cylinder. Next, solid cylinder inside hollow sphere. Inside hollow sphere. Okay. Like this. Of this. So here you consider this object 1 and this 2. Then you can easily comment that F22 inside object will have a 0. Okay, so F22 is equals to 0. F22 is 0, then F21 is equals to 1. Okay, then we can write F21 into A2 is equals to F12 into area of 1. So F21 1 into pi dl plus pi by 4 into d square plus pi by 4 into d square is equals to F12 into 4 pi r1 square. Now you take assumption that diameter of sphere is equals to 0.5. Sorry, sphere is inside, so you take it 1 meter, and length equals to dia equals to 0.5 for cylinder. So if you solve this, your F12 will be coming 3 by 8. Solve this. Are you getting the answer? Got this answer? So now F12 is 3 by 8. So you can calculate F11. It is equals to 1 minus 3 by 8. It is equals to 5 by 8. Okay. So in this way, you have to calculate the view factor. So view factor basically gives us idea actually that how much fraction of energy exchange is taking place between two objects. Okay. Got it? Okay. Next, we will see irradiation, that is denoted by G, and radiosity, that is denoted by J. Okay. So it is G watt per meter square. Here it is reflectivity, rho into G into emissivity. So this is total is known as radiosity J. So what is G? G equals to the radiation flux incident on a surface from all direction is called radiation. And J equals to the rate at which radiation energy leaves a unit area of a surface in all direction. Okay. Okay. So we are considering our object surface is opaque, means tau equals to 0, then alpha plus reflectivity is equals to 1. Surface is diffusive. Surface is gray, that is absorptivity equals to emissivity. So J equals to transmittivity कितना GI plus emissivity energy, total energy we are dealing. So J equals to 1 minus emissivity into GI. So it is transmittivity into GI. Okay. So in place of this, we can write 1 minus alpha, and in place of alpha, you can write this. So Ji equals to 1 minus emissivity into Gi plus emissivity into Eb. Okay, like this. So Q equals to Ji is total output minus input into flux. So Q equals to Ji. In place of Gi, we can write Ji minus emissivity into Eb, energy in that body, 1 minus alpha Ai. Okay. So Q equals to solve this Ji minus emissivity, Ji minus emissivity of black body upon, in place of alpha, you can write 1 minus emissivity. So Q equals to Eb minus Ji into emissivity into Ai upon 1 minus emissivity. So Q equals to energy in black body minus Ji upon 1 minus emissivity upon emissivity Ai. What is this? This is nothing but resistance. Okay, actually we want to convert this form into the form of energy here, delta, change in energy upon resistance, because we, you know, in conduction and convection what we have done, it is converted into delta T by R form. Okay, and for black body resistance is 0. Anna, for black body resistance is 0. Black body. As for that, we know emissivity is equals to 1. So if you put emissivity 1, it will be 0. Okay. So this is for gray body. Okay. So gray body, normally we do black body, we consider it as the ideal body. So gray body, you can say any body which is in contact with the atmosphere, we consider that body as a gray body. Okay. So write this. So when we have first case is two parallel black body like this. So here Q by A equals to sigma T1 to the power 4 minus T2 to the power 4. Second, black body inside black body. It is 1, it is 2. So Q upon A1 equals to sigma T1 to the power 4 minus T2 to the power 4. And Q by A2 equals to sigma F21 T2 to the power T1 to the power 4 minus T2 to the power 4. Okay, so depending upon in which area we want to calculate A1 or A2. If you are calculating A2, then you have to calculate F21. Okay, because here F12 is there and value of F12 is 1. So this is about black body. Write this. Okay. Now talking about two normal surface. So when they are parallel to each other, so Q by A is equals to sigma T1 to the power 4 minus T2 to the power 4 upon 1 upon emissivity 1 plus 1 upon emissivity 2 minus 1. Q by A1 is equals to sigma T1 to the power 4 minus T2 to the power 4. Okay. It is for when they are two normal bodies, one inside one another. So 1 upon sigma 1, emissivity 1, A1, A2, 1 upon emissivity 2 minus 1, like this. So write this. Okay. Now we will see radiation shield. So from the name itself, you can judge that radiation shield is to decrease the value of Q. So when you have two plates, in between, we will insert one plate. Okay. And this one plate will reduce the Q. Okay. So radiation shield for black bodies, radiation shield for black bodies. So it will be like this Q13. It will be like this Q32. Okay. So Q13, if we write, it will be sigma. We take a temperature T1, this is T2 and T3. So it is sigma T1 to the power 4 minus T3 to the power 4. Q23 is equal to sigma T3 to the power 4 minus T2 to the power 4. At steady state, you can just equate this. So sigma will cancel. So from here, T3 to the power 4 is equals to T1 to the power 4 plus T2 to the power 4 by 2. So if we put this Q with shield by A is equals to sigma T1 to the power 4 minus T3 to the power 4. So in place of T3, you write T1 to the power 4 minus T1 to the power 4 minus T2 to the power 4 by 2. So it will be sigma T1 to the power 4 minus T2 to the power 4 by 2. So it is just a half Q without shield by 2. Means there will be 50% reduction in the heat transfer. Whenever you enter one shield is basically it will act as a one protection to maintain the temperature inside the reactor. Okay. Okay. Now the same thing we can do for two normal plates. Like this. T1, this is T3, this is T2. So it will have some emissivity 1, emissivity 3, emissivity of 2, like this. So it will have some radiation like this. Okay. So we can write same equation which we have done previous. Q13 equals to sigma T1 to the power 4 minus T3 to the power 4 upon 1 upon emissivity 1 plus 1 upon emissivity 31 minus 1. Q23 upon A equals to sigma T3 to the power 4 minus T2 to the power 4 upon 1 upon emissivity 32 plus 1 upon emissivity 2 minus 1. Okay. Then we can write 13 upon A equals to sigma T1 to the power 4 minus T3 to the power 4, 1 upon emissivity 1 plus 1 upon emissivity of 3 minus 1. Okay. Q23 upon A equals to sigma T3 to the power 4 minus T2 to the power 4 upon 1 upon emissivity of 3 plus 1 upon emissivity of 2 minus 1, like this. Okay, so if you solve this, then width shield equals to sigma T1 to the power 4 minus T2 to the power 4 upon 1 upon emissivity of E1 plus 2 upon emissivity of E3 plus 1 upon emissivity of 2 minus 2. This is with shield. Okay, so write this. Okay. Then there is a case, suppose you have a black body and inside that you have a normal body. And this is black body. So you can write Q equals to sigma A1 emissivity 1 T1 to the power 4 minus absorptivity T2 to the power 4. Okay, you can write like this. Okay. Okay, then solve the question. Two black plates, each 1 meter square area, are parallel to each other in such a way that is radiation shape factor for the system is 0.4. If the plates are maintained at 800 degrees centigrade and 400 degrees centigrade respectively, determine the net radiation heat transfer between the plates. Okay. So if you solve this, Q by A is equals to F sigma T1 to the power 4 minus T2 to the power 4 is equals to 0.4 into 5.67 into 10 to the power minus 8. Always remember that in conduction and convection, there is no need to convert Celsius into Kelvin, but here you have to convert the temperature into Kelvin. So 1073 to the power 4 minus 673 to the power 4. That is equals to 25.41 kilowatt. Okay. Next question. Consider two flat parallel plate black maintain at a temperature of 1227 degrees centigrade and plate 2 is maintained at minus 174 degrees centigrade. If the another flat plate is introduced between two plates, so you have to calculate what is the temperature of plate 3. What is the percentage reduction in heat transfer? Solve this. Okay. So now you solve this. So first we have to solve the temperature T3. So T3 equals to under root of 4 upon 1500 to the power 4 plus 99 to the power 4 upon 2. So how much it will come? T3 is coming equals to 1261 Kelvin. So this is the temperature of plate 3. Now they have asked what is the percentage reduction in heat transfer. Okay. Percentage reduction in heat transfer. So percentage reduction Q, which sheet, what is the sigma 1500 to the power 4 minus 1261 to the power 4. Q without shield is equals to sigma 1500 to the power 4 minus 99 to the power 4 equals to 1500 to the power 4 minus 99 to the power 4 minus 1500 to the power 4 minus 1261 to the power 4 upon 1500 to the power 4 minus 99 to the power 4 into 100 will give you 50%. Okay, will give you 50%. So the answer is 50%, or you can directly say, okay, while derivation we have seen that if one plate is inserted, it will directly reduce the value of Q by 50%. There is no need to calculate also. Okay. Next question. A black body at a higher temperature energy to black body at a temperature lower body TL. Initially, TH equals to 1850 degrees centigrade and TL equals to 500 degrees centigrade. And the net rate of energy transfer is 25 watt. After some time, TH equals to 1500 degrees centigrade and TC equals to 750 degrees centigrade. What is the net rate of energy transformation? Solve this. So solve this. Basically, what is the effect in change in the temperature? What will be the new rate of heat transfer? Okay, so here Q equals to sigma A1 F12 equals to T1 to the power 4 T2 to the power 4. So here 25 equals to sigma A1 F12 equals to 1850 plus 273 to the power 4 minus 500 plus 273 to the power 4 upon it is equals to sigma A1 F12 1500 plus 273 to the power 4 minus 750 plus 273 to the power 4. So here Q equals to 11. Okay, so here Q equals to 11 watt per meter square. Next question. A small sphere of outer area is equals to 0.6 meter square is totally enclosed in a large cubicle hall. The shape factor of the hall with respect to sphere is 0.004. What is the length of the side of the cubicle? Calculate this. Okay. So here in this question, A12, okay, sorry, F12 into area of 1 is equals to F21 into area of 2. So it is 1, it is given, it is 0.6, okay, because it is insider, okay, that is why I have considered F12 equals to 1. It is 0.004 into area of 2. So area of 2, how much it is coming? To calculate, it will come 150. So 150 is equals to 6a square. So a equals to 5 meter. Okay. Cubicle hall, 6a square area. Next question. A plate having 10 centimeters square each side area is hanging in the middle of the room. 100 meters square. The plate temperature and emissivity are 800 Kelvin and 0.6. The temperature and emissivity value for the surface of the room is 300 Kelvin and 0.3. The total heat loss from the two surfaces of the plate is is 300 and 0.3. Solve this. So attempt this question. Okay. So here, see this. Q by A1 is equals to sigma T1 to the power 4 minus T2 to the power 4 upon 1 upon emissivity plus A1 by A2, 1 upon emissivity 2 minus 1. So here Q, here it is clearly mentioned that each side is 10 centimeters square, and here in the final answer they have asked from the two surface. Okay, final answer, two surface. Okay, so that is why here what will come, 2 into 10 to the power minus 4 for unit change, sigma 800 to the power 4 minus 300 to the power 4 upon 1 upon 0.6 plus 2 into 10 to the power minus 4 upon 100, 1 upon 0.3 minus 1. Now tell me what is the answer you are getting? What is the answer? What is the answer? So here the answer is coming 27.31 watt. So the most important thing here is this value. यहाँ पे गलती नहीं होनी चाहिए है ना, क्योंकि क्वेश्चन में उसने जो एरिया दिया वो ईस्ट साइड का दिया हुआ है ना. They have given area of east side. But while asking for the final answer, they have asked for two surface. Got it? Next question. An insulated cylindrical pipe of 0.2 meter dia has a surface temperature of 115 degrees centigrade. It is exposed to black body surrounding of 25 degrees centigrade. Emissivity and alpha is 0.96 and 0.93. The heat transfer coefficient outside the insulation surface is 3.25 watt per meter square Kelvin. Find the percentage contribution from the radiation to the total heat transfer rate to the surrounding. Okay, solve this. solve this. Okay, see this. Q through radiation is equals to sigma emissivity T1 to the power 4 minus absorptivity T2 to the power 4. So it is 5.67 into 10 to the power minus 8, 0.96. What is the temperature? 115 plus 273 to the power 4 minus 0.93 into 25 plus 273 to the power 4 is equals to 817 watt per meter square. Q convection is equals to 3.25 into 115 minus 25. It is equals to 292.5. Now you calculate this. What is the percentage from the radiation? It is 817 upon 817 plus 292 into 100 is equals to 73%. So there is 73% heat transfer through the radiation. So you have any doubt? Rio? Next question. Consider two black parallel plate. Plate 1 is maintained at 1227 degrees centigrade and plate 2 is maintained at minus 174 degrees centigrade. Okay. Calculate the net amount of energy exchange per unit area between two plates. Second, if the black plate or gray plate with an emissivity 0.8 and 0.7, calculate the net amount of energy exchange. Solve this. Means for first part you have to consider that it as a black plate, and for second part you have to consider it as a normal plate. So for first part, if you solve this, then Q by A is equals to sigma 1500 to the power 4 minus 99 to the power 4. So it is equals to 5.67 into 10 to the power minus 8, 1500 to the power 4 minus 99 to the power 4. So it is, how much it is coming? 287 kilowatt. Okay. Now solve for the second part. Okay, for second part, if you solve, it will be 5.67 into 10 to the power minus 8, 1500 to the power 4 minus 99 to the power 4 upon 1 upon 0.8 plus 1 upon 0.7 minus 1. So how much answer is coming? 171 kilowatt. Okay. So the last question, I will give it to you as a homework. I will tell you. Suppose you have a cylinder like this, and this is surface 1, this is surface 2, and this is surface 3. Okay. And it is given that F13 is equals to 0.17. So you have to calculate every value. F11, F12, F13 is given, F21, F22, F23, F31, F32, F33. Okay, so you have to solve this question. Take it as homework. So I will tell you how to solve. F13 you have. Okay. See, F11 is 0 here. F33 is 0 here. F22 is not equals to 0 because here, see, here it will go to here. Okay, on surface. This is circumference. Hai na? So as F11 is 0, you can directly apply F11 plus F12 plus F13 is equals to 1. You know F13, F11 is 0. You can calculate F12. Okay. Easily calculate. Now you have F13 into area of 1, F31 into area of 3. So A1 and A3 are same. So now you have a F31 value, which is equals to 0.17. So now you have F12, you can apply F12 into area of 1 equals to F21 into area of 2. So area of 2 will be pi dl and area of 1 will be pi by 4 into d square, and take d equals to L for this system. Okay, so you can easily calculate all the values. Okay, you can easily calculate all these values. Okay, so just for practice you can do. So here we complete the radiation topic. Okay, radiation topic we have completed. So here we are done with the heat transfer. Okay, so we have completed almost all the parts. I'm not say each and every topic is completed in a such less number of time, but we have tried to, I have tried to complete each and every topic here. Okay, so today all of we have done is the radiation. So if you have any doubt, you can ask. Okay, thank you, Rio. Okay, for attending the session and all. Hope you have enjoyed the session. Okay, so I have tried to cover all the things in short, except derivations. I have covered all things. Okay, so for revision, this is very good. Okay, so if you have any doubt, Rio, you can ask. Okay.